In today's class, we will be discussing Rydberg equation, we will be solving some problems, and we will be deriving the relation of radius, velocity, energy, etc. Okay, so let us start with the class. So the first thing that we will do is Rydberg equation, right? Now, according to Bohr, when an atom makes a transition from higher energy level to lower energy level, that is the Bohr's second postulate, right? It emits a photon with energy equal to the energy difference between its initial and final levels, right? So if EI is the initial energy of the atom before such a transition and E final is the final energy after the transition, then the photon's energy, that is E final minus E initial magnitude, is equal to hc by lambda, or you can say h nu, right? Now we know that for any state the energy is what, minus 13.6 multiplied by z square divided by n square. I have told you already that energy of any state is minus 13.6 divided by n square, right? This is for hydrogen atom. For any other atom, just multiply it by z square. So what I will write here is E initial is minus 13.6 divided by n2 square, right? Because we are assuming that the transition is from n2 to n1, okay? And the final energy is minus 13.6 divided by n1 square. So E initial minus E final can be written as, see, E initial minus E final can be written as 13.6 common, 13.6 common 1 by n1 square minus 1 by n2 square, and that is equal to hc by lambda. So hc by lambda is equal to 13.6 into 1 by n1 square minus 1 by n2 square into z square. So just take hc from here to here, right? You will get 1 by lambda is equal to 13.6 electron volt into z square divided by hc multiplied by 1 by n1 square minus 1 by n2 square. This whole term together, that is 13.6 electron volt divided by hc, is called the Rydberg constant, R. It is a constant, right? So the Rydberg constant value is 1.097 into 10 raised to power 7 per meter in SI units, right? This 1 by lambda is also called the wave number. This 1 by lambda is also called the wave number. Okay, lambda is the wavelength and 1 by lambda is the wave number. So the final relation comes out to be like this: 1 by lambda is equal to R into Z square into 1 by N1 square minus 1 by N2 square. Now this relation gives the wavelength of any transition from any state to any other state. But we have already remembered those values, right? We have already remembered the values of the wavelengths of each line, right? So when we will use this Rydberg equation, we will use this Rydberg equation when the ratio of the wavelength is asked. When the ratio of the wavelength is asked, in that case the values that we have learned will not be useful. Why? Because we have learned approximate values. That is why whenever they have asked you the ratio of wavelength, do not use the values that you have learned. Just take this simple Rydberg equation, and if you divide the wavelengths 1 by lambda 1 divided by 1 by lambda 2, you will directly get the value of the ratio. Okay. Sometimes wavelength is also written like this: lambda is equal to, just take this LCM and you will get n1 square n2 square divided by rz square into n2 square minus n1 square. The value of 1 by r is 0.91 into 10 raised to power minus 7 meter. Okay, so we will use Rydberg equation when first the ratio of wavelengths is asked, that we have already discussed, and second, sometimes what they will do is they will give you options and they will say that find the wavelength, and they will give the options in terms of the Rydberg constant. Obviously if they've given the value, means the answer in terms of Rydberg constant, then you will have to use this relation and you cannot use the remembered formulas. Okay, third, sometimes they give the value of Rydberg constant in the question. Sometimes they give the value of Rydberg constant in the question, and this value is slightly different from this that I have written here. Okay, and if the value of the Rydberg constant is different from this, suppose they have given 1.1, or 1.2 or even say only 1. Okay, in that case what will you do? You will use the Rydberg equation, because the learned formulas will not be useful then, because they have changed the value of the Rydberg constant. Okay, so if they give the value of the Rydberg constant in the question, in that case use Rydberg equation to find the wavelength. Let us do one question. Find the ratio of wavelength of second line of Balmer series of hydrogen atom to the third line of bracket series of He plus atom. Right? So here they have asked you the ratio. That means you have to use the Rydberg equation. You cannot use the formulas or the values that you have remembered. Okay. So first 1 by lambda 1, that is this wavelength, is equal to R into Z square. Z is 1 for hydrogen atom, into second line of Balmer series means 2 to 4. So that means 1 by 4, 1 by 2 square minus 1 by 4 square. Okay. Then the third line of bracket series. Now the bracket series starts from n equal to 4. So the third line means 4 to 5, 4 to 6, 4 to 7. Okay. That means 1 by lambda 2 will be equal to R into Z square. Z now is He plus Z is 2 into 1 by n1 square, that is 1 by 4 square, minus 1 by n2 square, that is 1 by 7 square. Okay. Now 1 by lambda 1 you have got, 1 by lambda 2 you have got. You just have to divide it. You will get the ratio lambda 2 by lambda 1 or lambda 1 by lambda 2, whatever they have asked you. Okay. I'm not calculating it. You can calculate it yourself. Now there's one more question. Suppose they have changed the value of R and they have given you, for simplicity purpose, the value of R is 1 into 10 raised to power 7 per meter. So if they have changed the value of R in the question, in that case, do not use the formulas that you have remembered. Okay, then you suppose they have asked you find the wavelength of the second line of Lyman series, then you will use the Rydberg equation only to find any line, right? So 1 by lambda is equal to R into Z square into 1 by n1 square minus 1 by n2 square. Now the second line of Lyman series means n1 is 1 and n2 is 3. So when you solve this, you will get 1 by lambda is equal to 9 by 8 into 10 raised to power 7. So lambda will be equal to 8 by 9 into 10 raised to the power minus 7. So this wavelength is different from what we have remembered, because they have changed the value of R in the question for simplicity purpose. In this question they have given you find the wavelength of radiation required to excite the electron in Li2 plus from the first orbit to the third orbit. So from the first orbit to the third orbit, you know that for a hydrogen atom you need 12.09 electron volt. So for Li2 plus, just multiply it with Z square. Okay. Then the second part is how many spectral lines, okay, are observed in the emission spectrum of the above excited system. So now it is excited to the third state. So from 3 to 1, the total number of spectral lines will be 3 lines. Okay. If you do 3C2 or 3 into 3 minus 1 by 2, you'll get 3 lines. Now in this question, they have given you, consider the following electronic energy diagram for a hydrogen atom. Photons associated with the shortest and the longest wavelengths would be emitted from the atom by a transition labeled. So they have not used n equal to 1, right? Now you know that the energy difference between two successive levels keeps on decreasing, right? As we go to the higher orbit. Now from here you can see this is Balmer series, this is Balmer series, right? And Balmer series, in any series the energy keeps on increasing, right? So this will have, this is the second line, so this will have more energy, and comparatively this is the first line of Paschen series, obviously this is less energy. So this is the maximum energy, and if this is the maximum energy, what they are asking you, photons associated with the shortest, so maximum energy means the smallest wavelength. So I'll write the smallest wavelength is C. So there first is the shortest, right? So the shortest wavelength is C, and this difference is not the minimum because this is n equal to infinity, not n equal to 5. Okay, now we know that this value is 0.66 and this value is 0.85. Why? Because n equal to 4 is 0.85. Okay, so that means this has the minimum value. So what you will say is the maximum energy is this, the minimum energy is this. But if minimum energy is this, that means the maximum wavelength is this. So I'll write C as the shortest wavelength and D as the longest wavelength. Okay. Now in the next question, it is given that a lithium atom has 3 electrons. So you know that the lithium atom has 3 electrons. Okay. Now in this question, they are giving you a hypothetical picture. Now, assuming the following simple picture of the atom, they are saying that two electrons move very close to the nucleus. Two electrons go very close to the nucleus and they make a spherical cloud around it, right? So in that case, what you have to do is you have to find the Z effective. And the original Z of the original Z means what? Proton number. Actually Z means what? The net nuclear positive charge. Okay, now in this case lithium atom has 3 protons, so 3 positive charge, but there is 2 electrons also forming this electron cloud. So in that case you will say that Z effective is equal to 3 minus 2 and that is equal to 1. Okay, so in this case the Z effective is actually 1 and not 3. Now there is one more electron and it is revolving. So here 2 electrons have come inside the nucleus and 1 electron is revolving. So this is a hypothetical picture. Okay, now 1 electron is revolving and in this question they are given to you that n equal to 1 state is not available to it. This electron cannot remain in n equal to 1 state in this hypothetical model because the electron cloud has formed here and it is destabilizing the first orbit. Okay, so n equal to 1 is not available, only n equal to 2 is available. So in that case calculate the ionization energy of the lithium in the given picture. So in that case, what you will do, you know that the ionization energy starts from 1 to infinity, but in this case, it does not have n equal to 1 as a possibility. So what will you do is you will start from n equal to 2 and n equal to 2 is minus 3.4 into Z effective square and Z effective here is 1. So that means the energy of the second orbit is minus 3.4 electron volt, right? So if the energy of the second orbit is minus 3.4 electron volt, then from minus 3.4 electron volt to 0, the energy required is 3.4 electron volt. So the ionization energy of this hypothetical model is 3.4 electron volt, right? Now let us look at this next question. In this question, it is given to you that the energy levels of a hypothetical 1 electron atom. So this is also a hypothetical atom. Okay, and in this hypothetical atom, they have given you the energy levels of the different states. Okay, then first thing that they are asking is find the ionization potential. Ionization potential is 1 to infinity. Infinity is still 0. Okay, so if the infinity is still 0, in that case what will you say? You will say that the ionization energy is 15.6 electron volt. So obviously the ionization potential will be 15.6 volt. So the first one was pretty simple. Then the question part B is find the short wavelength limit of the series terminating at 2. Now the series terminating at 2, that means the Balmer series, and they are saying is the short wavelength limit. The short wavelength limit means the smallest wavelength. The smallest wavelength means maximum energy. Okay, so I will write from here the smallest wavelength means maximum energy. So B part, this is the A part, and if I write the answer of B part, I will write 1240 divided by 2 to infinity, and that is 5.3. So this is the wavelength. Okay, I'm not calculating it, you can do it yourself, right? Then the third question is find the excitation potential for the state n equal to 3. The excitation always starts from n equal to 1. Now if the excitation always starts from n equal to 1, that means the first excitation potential will be 1 to 2, the second will be 1 to 3, The third excitation potential will be 1 to 4, but they have not asked the third excitation potential. Actually here they are saying that the excitation potential for the state n equal to 3, that means the second excitation potential. So the second excitation potential means 1 to 3. Now from 1 to 3, you can see that the energy required is 15.6 minus 3.08. I'm not calculating it, you can do it yourself. Okay, then the fourth part of this question is find the wave number of the photon emitted for the transition 3 to 1. So 3 to 1, obviously 3 to 1 energy will be emitted, and 1 to 3 same amount of energy will be absorbed. So that means the answer that you have got here is the energy. What you have to do now is find the wavelength. So what you do? You will say Hc divided by 15.6 minus 3.08 is the wavelength. Okay, but they have asked you the wave number. What you do? Find 1 by lambda. Okay, find 1 by lambda. Now the next part of the question is very important. Listen carefully. What is the minimum energy that an electron will have after interacting with this atom in the ground state if the initial kinetic energy of the electron is 6 electron volt or 11 electron volt? Now this is a very important question. So there are two cases here. An electron is colliding with this hypothetical atom. Okay, so the electron, if it collides with this hypothetical atom, they have given you two cases. In the first case, the kinetic energy of electron is 6 electron volt. Okay, and the minimum energy required for excitation is 10.3 electron volt, 1 to 2, because every atom we will assume that it is in the ground state. So if you want to excite it from 1 to 2, you will need at least 10.3 electron volt energy. So the minimum energy required for excitation is 0.3 electron volt. Okay, but the kinetic energy of this electron is only 6 electron volt. That means this electron cannot excite the atom. Now if this electron cannot excite the atom, that means this electron will not lose energy, because the energy will be lost only if there is a transition. Okay, so the electron will not lose energy, I'll write it again here. Listen carefully. In atomic collisions, energy is lost only if there is a transition. If there is no transition, you will not say that energy is lost. Okay, so only if there is a transition. This is a very important point that we will discuss again in atomic collision. So in atomic collision, energy is lost only if there is a transition. Okay, now in this case the transition is not possible, so the electron will not lose energy. So you will say that the final energy of electron is 6 electron volt only. Okay, but there is a B part here, and in this B part the energy of the electron is 11 electron volt. Now the kinetic energy of the electron, if it is 11 electron volt, then what you will do, then it can excite. And if it excites, then what will you say? If it excites, then 10.3 electron volt energy is lost in excitation. So the remaining energy of electron will be equal to 11 minus 10.3, and that will be equal to 0.7 electron volt. So electron will give its energy to the atom only if it is possible to excite. Okay, if it is not possible to excite, then the electron will not lose any energy. This is very important. In an atomic collision, there is loss of energy only if there is a transition. If there is no transition, then there will never be any loss of energy. Okay, now in the next question, it is given to you that a gas of hydrogen like atom can absorb radiation of 68 electron volt. So this is a very important question. Everybody listen to me very carefully. A gas of hydrogen like atom. So they have said that it is a hydrogen like atom and it is not the hydrogen atom. And it can absorb radiations of 68 electron volt. So that means this hydrogen like atom. So this is the hydrogen like atom, and it absorbs 68 electron volt energy, but they have not given you the state. Okay, consequently the atom emits radiations of only 3 different wavelengths, right? So that means they are saying that on de-excitation, only 3 wavelengths are emitted. Only 3 wavelengths are emitted. Okay. Now, when the hydrogen-like atom has absorbed 68 electron volt energy, let us assume that it moved from N1 to N2. They have not given you that the hydrogen-like atom was in the initial state, right? So I'll assume that it was initially at N1 and finally at N2. So due to this absorption of 68 electron volt, it moved from N1 to N2. But because only 3 wavelengths are emitted, that means N2 has to be equal to 3, because 3 wavelengths means 3 lines, right? And 3 lines means N2 has to be equal to 3. Okay, so the value of N2 now we already know. The value of N2 is 3. So now N1 can be either 1 or 2. N1 can be either 1 or 2. Okay, N1 can be either 1 or 2. Now let us see here. See what they have given you in the next line. This is very important. All the wavelengths are equal to or smaller than the absorbed photon. That means whatever wavelength that the excited atom is emitting is smaller than or equal to that of the absorbed photon. So now absorption, if 1 to 3, because you know that the final state is 3, then you will say it will have maximum energy and minimum wavelength. And from 2 to 3, from 2 to 3, you will say that it has minimum energy and maximum wavelength. Okay, now emission, when there is emission, then it will be 3 to 2, 2 to 1 and 3 to 1. Obviously all these 3 lines will not come from the single atom. Okay, there are many atoms, there are crores of atoms. So 3 to 2 will be the minimum energy, and this will be the maximum energy of the emitted rates, okay, of the emitted radiations. Now again I'll repeat this question. All the wavelengths that are emitted are equal to or smaller than that of the absorbed photon. So from this, what are you getting? See, wavelengths are equal to or smaller than that of the absorbed photon. That means the absorbed photon must have maximum wavelength. Absorbed photon must have maximum wavelength. Okay, now if the absorbed photon has maximum wavelength, that means it has to be 2 to 3, because 1 to 3 it will have minimum wavelength, right? So that means from here what will you say? Therefore N1 is equal to 2, right? So N1 is equal to 2, and from 2 to 3 transition, the hydrogen-like atom is absorbing 68 electron volt. Now, you know that for 2 to 3, so I'll write again here, N1 is 2. So for 2 to 3, what will you say? The energy for the hydrogen atom is 1.89. But for the hydrogen-like atom, it will be 1.89 into Z square. But according to question, this is 68. From this, when you solve this, you will get Z is equal to 6. So if Z is equal to 6, then identify the gas atoms. So the gas atom is carbon. Determine the initial state of the gas atom. That means N equal to 2. Find the maximum wavelength of the emitted radiation. Now the maximum wavelength of the emitted radiation will be, see, the maximum wavelength will be obviously this one. This one is minimum energy, so maximum wavelength, right? So the maximum wavelength will be, the maximum wavelength will be, so for 3 to 2 transition, for hydrogen atom it is how much? It is the first line of Balmer series. The first line of Balmer series, the wavelength will be how much? The wavelength will be 656 nanometer, right? But this is not hydrogen atom, this is hydrogen-like atom whose Z we have already calculated. So just divide it by Z square and that is 36. So this is the maximum wavelength, right? Sorry, they have asked you the minimum wavelength of the emitted radiations. So now we will find the minimum wavelength of the emitted radiations. So the minimum wavelength means the maximum energy, right? The maximum energy is from 1 to 3. Okay, so the minimum wavelength will be 1 to 3 transition. That means the second line of Lyman series. So it is 102 nanometer divided by 36. Okay, the next thing that they have asked is find the ionization energy and the respective wavelength for the gas atom. So what is the ionization energy? The ionization energy is 13.6 multiplied by Z square. Okay, and the wavelength corresponding to this is so 13.6 means 91 nanometer for hydrogen, thus divided by 36 you will get the wavelength for this particular atom, that is Z equal to 6. Okay, you can join me on Telegram and ask your doubts there, the link of which is given in the description box. In this question, it is given that a gas of hydrogen-like atoms has some atoms in the lowest energy level A and some atoms in a particular excited level B, and there are no atoms in any other energy levels. The atoms of the gas makes a transition to a higher energy level by absorbing the monochromatic light of photon energy 2.7 electron volt. So that means 2.7 electron volt energy is absorbed by this atom, okay, and it reaches from N1 to N2. They have not given you the states. Okay, the atoms emit radiations of only 6 different photon energies. So that means what they are saying is when it de-excites, it emits photons of 6 wavelengths. That means 6 lines. So if 6 lines are observed, then we have done so many questions now. So if 6 lines are seen in the emission spectrum, or you can say if 6 photons are emitted or 6 wavelengths are emitted, then N2 has to be equal to 4. Okay, so that means now what information that we have is 2.7 electron volt absorption leads to N1 to 4. Okay, so the electron transits from N1 to 4. Okay, now subsequently the atoms emit radiation of only 6 different photon energies that we have discussed. Now some of the emitted photons. So first of all, what can be the absorbed photon? First, let us see what can be the absorbed photons. So the absorbed photons can be 2 to 4 or 3 to 4. We don't know yet. We don't know the value of N1 yet. So it can, by absorbing 2.7 electron volt, it can either move from 2 to 4 or 3 to 4. We still do not know. Okay, but you know that when there is emission, there are 6 lines corresponding to 4 to 3, 4 to 2, 4 to 1, 3 to 2, 3 to 1 and 2 to 1. So these are the 6 lines in the emission spectrum. Okay, now what is the information that is given here? Some of the emitted photons have energy 2.7 electron volt. That means some of the emitted photons will have energy of the absorbed photon, and that is true because out of this 6, one of them has to be this. See, if it is 2 to 4, here there is this one 4 to 2. If it is 3 to 4, here there is 4 to 3 also, right? So this is obviously known to us. Some of the emitted photons have energy 2.7 electron volt. Now some have energy more, and some have energy less than 2.7 electron volt. Now, see, they are saying that in this spectrum, in this emission spectrum, some of them have energy should be more or less than absorbed photon, or equal to. Okay, now let us look at the absorbed photons. Let us first look at 3 to 4. If you look at 3 to 4, you will see that 3 to 4, out of all these photons, 3 to 4 has the minimum energy. If out of all these photons, 3 to 4 has the minimum energy. So if the absorbed photon is 3 to 4, in that case you will say that the emission spectrum will not have any energy which is lower than this. But that should not be the case. Why? Because energy should be more or less than absorbed photon or equal to the absorbed photon. That means in this spectrum there should be some energy which is more than the absorbed photon and some energy which is less than the absorbed photon. So if the transition of the absorption spectrum was from 3 to 4, that means by absorbing 2.7 electron volt, if the transition was from 3 to 4, in that case here in the emission spectrum there will be no energy which is less than this, right? Because this is the minimum. So this is not possible, because it is clearly mentioned that there should be energy which is more, less and equal, all. So that means the transition has to be from 2 to 4. So if you see from 2 to 4, then there will be some energies which is more than this, right? For example, 4 to 1, 3 to 1, 2 to 1, all these are energies more than this. Okay, and 4 to 3 is energy which is less than this. So definitely the answer should be 2 to 4. Okay, because this is the middle energy. So in the emission spectrum there will be energy which is more than this and there will be energy which is less than this. So you will say that the value of n1 has to be 2, right? So let us look at the question again. Find the principal quantum number of the initially excited level B. So that will be 2, right? So the first part answer will be 2. Initial excited energy level was 2, and after absorption of 2.7 electron volt, the excited energy level became 4. Find the ionization energy for the gas atoms. Now this is a difficult question. This is a hydrogen-like atom, right? It is not a hydrogen atom, but still the energy is somewhat close to the hydrogen atom only. See, 2.7 electron volt, and actually if it was hydrogen atom, it was 2.55 electron volt, right? So this is a atom which is similar to hydrogen atom only. Okay, so now they have asked you the ionization energy. Now what I will do is, listen carefully, I will say that it is given to us that E2 minus E4 is equal to 2.7. So let the ground state energy be E. Okay, let the ground state energy be E. So from this I will write E by, I'm just writing the magnitude. Let the magnitude of ground state energy be E. From this I will write E by 2 square minus E by 4 square is equal to 2.7, and from this I will get E is equal to 14.4 electron volt. Okay, so from this I will get E is equal to 14.4 electron volt. That is the energy of ground state is, minus 14.4 electron volt. Okay, now this is the energy of the ground state, and so this is different from hydrogen atom, right? Because in hydrogen atom the energy of ground state is minus 13.6. Okay, but you know that energy of any other state is energy of ground state divided by n square. So I've used that concept here. So we have got the energy of the ground state, and ionization energy is what? 1 to infinity. Now infinity has energy 0. Okay, so if infinity has energy 0, so I'll write the ionization energy is 14.4 electron volt. Now let us look at the next question. they are asking you find the maximum and the minimum energies of the emitted photon. Now the maximum energy will be from 4 to 1 and the minimum energy will be from 4 to 3, right? So I'll write the maximum energy will be from 4 to 1, that is 14.4 into 1 minus 1 by 16, right? Because I'm just doing the energy difference, right? Energy from 4 to 1. So that means fourth level has energy 14.4 divided by 4 square. And the first level has energy 14.4. And the minimum energy will be 3 to 4, right? So minimum energy will be 14.4 into 1 by 9 minus 1 by 16. So this is the maximum energy and this is the minimum energy. So in this case, the remembered formulas will be not much of a use. And actually, I'll tell you, this atom is a deuteron. Okay. So this is actually like this 1H2. In this question, it is given that a hydrogen atom in ground state absorbs a photon of ultraviolet radiation of wavelength 50 nanometer. Assuming that the entire photon energy is taken up by the electron, with what kinetic energy will the electron be ejected? Okay, so in this question, it is given that the hydrogen atom is absorbing a photon which has energy 50 nanometer. So that means if you do E is equal to hc by lambda, I'll get 1240 divided by 50, and that will come out to be 24.8 electron volt. Okay. Now, assuming that the entire photon energy is taken up by the electron, so if all of this energy is taken up by the electron, then obviously it will ionize. Atom will ionize. Okay, so if the atom will ionize, then the remaining energy will be 24.8 minus 13.6, because the ionization energy is only 13.6, and that will come out to be 11.2 electron volt, and this energy comes as the kinetic energy of the electrons. Okay, so this energy comes as the kinetic energy of electrons. So what will be the kinetic energy of the ejected electron? The answer will be 11.2 electron volt. Okay. Now, the next question is, a monochromatic light source of frequency f illuminates a metallic surface and ejects photoelectron. So in this question, it is given that there is a monochromatic light source and the frequency is given as nu, right? Or f, you can use f or nu, illuminates a metallic surface and ejects photoelectrons. The photoelectrons having maximum energy are able to ionize the hydrogen atoms. So that means what they are saying is Ke max is equal to 13.6 electron volt according to question. Okay, so according to question, the Ke max is 13.6 electron volt, because what they are saying is the photoelectrons having the maximum energy is just able to ionize the hydrogen atoms in the ground state. Now, when the whole experiment is repeated with an incident radiation of frequency 5 nu by 6, then the photoelectrons so emitted are able to excite the hydrogen atom beam, which then emits a radiation of wavelength 1 to 1.5 nanometer. Okay, then find the work function and the frequency. So now, if the frequency is nu, in that case the Ke max is 13.6. If the frequency is 5 nu by 6, in that case what they are saying is 121.5 nanometer is emitted when it excites and then again it de-excites. You know that if it is 121.5 nanometer, from this clearly we can see this is the first line, right? This is the first line of Lyman series. Now the first line of Lyman series has energy how much? 10.2 electron volt. So what I will say is, if the frequency is 5 nu by 6, then the Ke max is 10.2 electron volt. Okay, now if you use the Einstein's photoelectric effect equation, then I'll write h nu is equal to 5 will be same for the metal plus 13.6, and 5 h nu by 6 will be equal to 5 plus 10.2. Now when you make a difference, then you will get h nu minus 5 h nu by 6 will be h nu by 6 is equal to 13.6 minus 10.2, and that will be equal to 3.4. So from this we will get h nu is equal to 3.4 multiplied by 6, and that will be equal to 20.4 electron volt. Okay, so from this you have got the value of the energy of the photon. Okay, and from this you can calculate the value of phi. I'll not do it further, you can do it yourself. You can calculate the value of phi, and you can also calculate the value of the frequency. Let us look at this question. In this question it is given that a stationary He plus ion emitted a photon corresponding to the first line in Lyman series. Right? The photon liberated a photoelectron from a stationary hydrogen atom in the ground state. Then find the velocity of the photoelectron. So what they're saying is, there is a stationary He plus ion. It emitted a photon corresponding to the first line in Lyman series. That means it de-excited from 2 to 1. Okay, the photon liberated a photoelectron from a stationary hydrogen atom in ground state. Then find the velocity of the photoelectron. So 2 to 1, that means the energy emitted is 10.2 multiplied by 4, or 10.2 multiplied by z square. 10.2 is the energy that is emitted for a hydrogen atom, and multiplied by z square. So from this you will get 10.2 multiplied by 4 is 40.8 electron volt. So this is the energy emitted. Now this energy strikes a hydrogen atom. So if this energy strikes a hydrogen atom, that too in ground state, you know that it will ionize. Why? Because this energy is sufficient to ionize hydrogen atom. So this hydrogen atom will ionize, and because it requires only 13.6 electron volt, okay, but their energy is excessive, so the remaining energy, that is 40.8 minus 13.6, this will be the kinetic energy of electrons. Okay, now once you get the kinetic energy of electrons, you can use K is equal to half mv square to get the velocity of the photoelectrons, right? But remember, write this kinetic energy in joules. You know that 1 electron volt is 1.6 into 10 raised to power minus 19 joules. And you also know that the mass of electron is 9.1 into 10 raised to the power minus 31 kg. So from this you will get the velocity of the photoelectrons, right? Now we will discuss the Bohr's third postulate. And the Bohr's third postulate is also called the quantization of angular momentum. Okay, now Bohr found that the magnitude of the electron's angular momentum is quantized. Now quantized means fixed or discrete values, and this magnitude for the electron must be an integral multiple of h upon 2 pi. Now the angular momentum of an electron about the center is, you know that the angular momentum is mr cross v. Now r and v are perpendicular to each other, so it can be written as mrv or mvr, right? So the angular momentum mvr of an electron is equal to nh upon 2 pi. This is the Bohr's third postulate, that is the quantization of angular momentum. So what he said was, the angular momentum of every orbit is fixed, or you can say quantized, if and it has to be an integral multiple of h upon 2 pi. That means for the first orbit, so the angular momentum of the first orbit is h upon 2 pi. The angular momentum of the second orbit is 2h upon 2 pi. The angular momentum of the third orbit is 3h upon 2 pi. Okay, but there is one more important thing that you should remember here, and that is it is independent of z. That means for every hydrogen-like atom, the angular momentum will be same. For every hydrogen-like atom, the angular momentum will be same. Okay, so the angular momentum postulate is mvr is equal to nh upon 2 pi. Okay, so n represents the orbit number. If first orbit n equal to 1, second orbit n equal to 2, third orbit n equal to 3. Okay, and what is this velocity? Velocity is the velocity of electrons in the nth orbit. R is the radius of the electron in the nth orbit. That is why we will write it like this, so that it is more clear, and we will write mvnrn is equal to nh upon 2 pi. Right? Now this postulate was proved by de Broglie using the concept that the electrons has wave nature. Now you know that all matter has wave nature, and de Broglie was the first scientist to say this. Okay, now what he used was an electron is revolving around the atom, and it also has a wave nature. Now according to de Broglie, there must be an integral multiple of wave in each orbit. If there is an integral multiple of wave, in that case there will be constructive interference and it will be stable. Okay, there will be constructive interference and the orbit will be stable. If the wave is not an integral multiple of the wavelength, in that case what will happen? There will be destructive interference and the orbit will be unstable. Okay, and he said that the first orbit will have one wave, the second orbit will have two waves, the third orbit will have three waves, and the nth orbit will have n waves for constructive interference. So if there is constructive interference, then that orbit is stable. So we now know how and which orbits can become stable when there is an integral multiple of the electron wave. One wave means one wavelength. One wave means one wavelength. So if one wave means one wavelength, that means if there are n waves, that means n wavelengths. Okay, so this total length will be L lambda, but this total length is also equal to 2 pi Rn, right? Where Rn is the radius of the nth orbit. So I'll write 2 pi Rn is equal to L lambda, and from this you will get 2 pi Rn is equal to, you know that lambda is h upon mv. So lambda is equal to h upon mvn, right? When you take this mvn this side and 2 pi this side, you'll get this Bohr's third postulate, right? So sometimes they ask you question from this also. They ask you what is the wavelength of the electron wave. Okay, or if they've given you the wavelength of the electron wave, from this they will ask you the radius of the orbit. Okay, they can also ask you the orbit number. They can ask you anything. This relation is also very useful. This question has been asked many times. Okay, so de Broglie was the scientist who proved the third postulate of Bohr. Bohr said that the angular momentum was quantized, but he did not prove it, and it was proved by de Broglie. Now we will derive the radius, velocity, time period, energy, and magnetic moment of hydrogen and hydrogen-like atoms in any orbit. Right? We know the Bohr's quantization of angular momentum, that is the Bohr's third postulate, is mv and rn is equal to nh upon 2 pi. So this is the first equation. And we also know that the electrostatic force of attraction is providing the centripetal force for the revolution of the electron around the nucleus, right? And that electrostatic force is K. K can be written as 1 by 4 pi epsilon naught Q1. Now the charge of this is ZE. Q2, the charge magnitude is E. So K, Q1, Q2. Q1 is ZE, Q2 is E. So I've written ZE square divided by R n square. So this is the force, right? Is equal to mv square by R, because the centripetal force is mv square by R and the electrostatic force of attraction is providing the centripetal force. Now when we solve this two equation, we will get the radius is equal to epsilon naught n square h square by pi me square into z, and velocity will be e square z by 2 epsilon naught nh. Okay, but now we will look more into details of radius and velocity. Okay, first let us look at this radius formula carefully. Now the radius can also be written as epsilon naught h square by pi me square into n square by z. I have separated the constant terms and the variable terms, where n is the orbit number and z is the atomic number. Okay, now this term is sometimes written as R naught or A naught, where A naught is 0.529 angstrom because all these terms are constant. So A naught is, if you put n is equal to 1 and z is equal to 1, then the radius will be A naught. That means the value of A naught is the radius of electron in the first orbit of hydrogen atom is 0.529 angstrom. So the radius of electron in the first orbit of hydrogen atom is A naught and its value is 0.529. Okay. Now the radius is proportional to n square by z. Okay. So sometimes they also ask you the proportionality. So the radius is proportional to n square by z, and you have to remember this proportionality, and the value of R naught is 0.529 and radius is proportional to n square by z. So if they ask you the ratio of two radius, you will write Rn1 by Rn2. That means radius in orbit n1 to radius in orbit n2 will be equal to n1 square by z1 divided by n2 square by z2, and that will be equal to n1 square by z1 into z2 by n2 square. Now if you have a hypothetical atom, now this is very important, listen carefully. If you have a hypothetical atom where the revolving particle is not an electron but some any other particle, it can be any particle, they'll give you any name. Okay, name does not matter. I'm just saying it is a hypothetical atom where the revolving particle is not an electron but any other atom. So for a hypothetical atom, suppose the mass of the revolving particle is x times the mass of electron. So the revolving particle, the particle which is revolving, does not have the mass same as the mass of electron, but it has a mass which is x times the mass of electron. And the charge of the revolving particle is y times the charge of electron. So the revolving particle which is revolving around the nucleus has a charge which is y times the charge electron. Then what is the value of Rn for this hypothetical atom? Now the answer lies here, R naught. Now this R naught, you can see that this R naught is inversely proportional to me square. Now instead of m, if I write xm, and instead of y, if I write ye, then it will become epsilon naught h square by pi me square will remain intact, but there will be one new term xy square, right? So here we will say that this is equal to epsilon naught h square by pi. Instead of m I have written xm, instead of e I have written ye, and I will get epsilon naught h square by pi me square as it is, but there will be one more term called 1 by xy square. Okay, but this term is R naught, where R naught is 0.529. So the radius of electron in the nth orbit for this hypothetical atom is R naught by xy square into n square by z. Now you can easily do this when you remember this R naught value, or even if you remember the proportionality with m and e square. Okay, R naught is inversely proportional to me square. Right? For simple normal atom, m and e you know, but for a hypothetical atom they can give you anything. Okay. Now similarly, now we will find the velocity. Velocity is z square by 2 epsilon naught nh, right? Okay, we will elaborate it further. See, the velocity is equal to e square by 2 epsilon naught h into z by n. Now, this term is called V naught. We have separated the constant term and the variable terms. This term is V naught, and V naught is 2.18 into 10 raised to power 6 meter per second. Again, if I put Z equal to 1, if I put N equal to 1, what will I get? I will get the value of V as V naught, right? If N is 1, that means first orbit. If Z is 1, that means hydrogen atom. So I'll write V naught is the velocity of electron in the first orbit of hydrogen atom. Okay, so V naught is the velocity of the electron in the first orbit of hydrogen atom, right? So I'll write this velocity again as V is equal to V naught into Z by N, where the value of V naught is 2.18 into 10 raised to power 6 meter per second, right? Now, what is the ratio? If they ask you the ratio, so in that case, this time the proportionality is Z by N. So I'll write V1 by V2 is equal to Z1 by N1 into N2 by Z2. Okay. This time, if you see carefully here, you will see that there is no term of mass. So V naught is independent of mass. So if the mass of the revolving particle changes, even then there will be no change in the velocity of the revolving particle. There will be no change in the value of velocity in any orbit if you change the mass, right? So for a hypothetical atom, this time you will only change this E square with YE whole square, that is Y square. Mx will not come here. Okay, so you will say that the velocity of the hypothetical atom will be y square times the original velocity. So y square times v naught into z by n. This is the velocity of electron in the nth orbit of a hydrogen like atom. Okay, now this is very important. V naught is independent of mass. So if the mass of the revolving particle is changing, but the charge is not changing, then there will be no change in velocity. So many questions are asked in this pattern where they say that the charge is same, but the mass is become twice. Then what will be the change in the velocity of the electron? There will be no change in the velocity of the electron. Okay, so velocity of electron means velocity of the revolving particle does not depend on mass. Okay, now the next thing is the time period. The time period of revolution is 2 pi Rn by Vn, right? Now 2 pi is a constant. Rn we already have calculated. Rn is epsilon naught h square by pi me square into n square by z divided by Vn. Vn is what? Vn is e square by 2 epsilon naught h into z by n. Okay, so from this pi cancel and I will get 4 2 multiplied by 2 4 epsilon naught square h cube divided by m e square into e square, that is m e power 4 into n cube by z square. So the time period is 4 epsilon naught square h cube divided by m e power 4 multiplied by n cube by z square. Again, I have separated the constant terms and the variable terms, and this constant term together is called T naught, where again T naught is the time period of electron in the first orbit of hydrogen atom. And when you put all these constant values, you will get T naught is equal to 1.52 into 10 raised to power minus 16 second. This is the value of the time period of electron in the first orbit of hydrogen atom. So you'll write the time period as T naught into n cube by z square. You have to remember the proportionality for each of the case. Okay, so the time period is proportional to n cube by z square. If you remember other things, that is very good. That is an added benefit, but this is the necessity. You have to learn the proportionality. The time period is proportional to n cube by z square. So that means you can say that T1 by T2 is equal to n1 cube by z1 square into z2 square by n2 cube. Okay, now for a hypothetical atom, this time you can see here function of m e power 4, right? So from this I will say that if it becomes xm and if it becomes ye, then there will be an extra term of xy power 4 in the denominator. So I'll write for a hypothetical atom, the time period is T naught by xy power 4 into n cube by z square. Okay, every time you have to pause it, you have to write it, you have to remember it, and then only you can proceed to the further part of this lecture. Okay, the next thing that we will discuss is the frequency, and the frequency is very simple. Frequency is 1 by time period. Okay, now frequency is 1 by time period. That means if time period is proportional to n cube by z square, frequency will be proportional to z square by n cube, right? And from here just reverse it and you will get the frequency. So frequency will be m e power 4 divided by 4 epsilon naught square h cube into z square by n cube. Okay, Then there is omega. Omega is 2 pi f, angular frequency. So sometimes they can ask you angular frequency. Angular frequency is also proportional to z square by n cube. You just have to multiply it with 2 pi. So when you multiply this with 2 pi, you will get me power 4 by 2 epsilon naught square h cube into pi into z square by n cube. Okay. Then there is kinetic energy. Now you know that kinetic energy is half mv square, right? And we have already calculated the value of velocity. And what is that value? E square by 2 epsilon naught h multiplied by z by n. Okay. So if you do v square, so I'll write again, v is E square by 2 epsilon naught h into z by n. If you do v square, you will get e power 4 divided by 4 epsilon naught square h square into z square by n square. So I've just written this here. And multiply this by half m, you will get the kinetic energy, and that will be equal to m e power 4 divided by 8 epsilon naught square h square into z square by n square. Okay, for kinetic energy, I want all of you to remember this k naught. Okay, again this k naught is the kinetic energy of the electron in the first orbit of hydrogen atom. I want you to remember the value as well as this relation also, or at least this proportionality and this denominator coefficient term. Okay, so the value of k naught is 13.6 electron volt, and this can also be written as 2.18 into 10 raised to the power minus 18 joule. What I have done here is I have multiplied this with 1.6 into 10 raised to the power minus 19, because 1 electron volt is 1.6 into 10 raised to the power minus 19. So here kinetic energy of a hypothetical atom is equal to, from here it will be equal to xy power 4 into k naught into z square by n square. So this is the kinetic energy of a hypothetical atom, right? Now the next thing that we will discuss is the potential energy. Okay, now kinetic energy is always positive and has absolute value, but potential energy is not like kinetic energy. Unlike kinetic energy, potential energy does not have any absolute value. Okay, in a system, so in a system, depending on the choice of reference, this point can have any potential energy. This point can have any potential energy. Okay, so potential energy absolute value is actually not defined. The potential energy is always defined as difference between two positions, right? Potential energy difference is always defined, but the absolute value is actually not defined. So what I mean to say here is, suppose the potential difference between these 2 points. Now potential energy difference in a system is fixed. Potential energy difference is fixed, but there is no absolute value. What I mean to say is, if this is the difference between these 2 points, the potential energy difference between these 2 points is 10 joule. Then if this is 0, this has to be 10. If this is minus 10, this has to be 0. I'm assuming this has the higher potential energy. If this is minus 20, this has to be minus 10. If this is 10, this has to be 20. So the potential energy absolute value has no meaning. Okay, it has meaning only if it is calculated as a difference. Okay, so absolute value of potential energy does not exist unless you define a reference system. So the next point is to define the absolute value of potential energy, because we have calculated the potential energy of the spring as half kx square. We have calculated the potential energy between two charges as k q1 q2 by r, right? But there we have taken a reference point and we assign zero value at of potential energy at the point of reference. For example, in an electrostatic system, we define infinity as the reference point. Why? How to choose this reference point? Okay, there is no definite method, but whatever formulas that we have a fixed set of system, and we have always chosen reference point as that point where the value of the force is 0. So for example, if the electrostatic force is k q1 q2 by r square, then when r is infinity, the force becomes 0. So the reference point is chosen as infinity. All right. So Now, if one point has fixed potential energy, because the difference has to be fixed, the difference has to be fixed. If one point is fixed, all other points becomes fixed because the difference has to be fixed. So that is why if you define potential energy to be zero at the reference point, then all the points will now have absolute value. Okay, so here, see, to define absolute value of potential energy, we take the reference point and assign zero value of potential energy at the point of reference. So we assign zero value of potential energy at the point of reference, and with respect to that point, potential energy of all other points are defined. Okay, and this becomes an absolute value. Now, for electrostatic system, we take the infinity as the reference point and assign zero value at that point. So for electrostatic system, we take infinity as the reference point and assign zero value at that point. I have told you why we take infinity as the reference point. And for an electrostatic system, we have already derived the potential energy between 2 point charges when we studied electrostatics, right? So the potential energy is equal to, so again I am writing it as a difference first because potential energy is always defined as difference. So U minus U infinity, infinity is the reference point, is equal to K Q1 Q2 by R. But this is zeros, that is why I have written U here. So U is equal to K Q1 Q2 by R. Now, K is 1 by 4 pi epsilon naught, right? Q1 is ZE, Q2 is minus E, and R is Rn. So from this you will get the value of potential energy is minus ZE square by 4 pi epsilon naught Rn. Okay, from this you will get U is equal to minus ZE square divided by 4 pi epsilon naught into Rn. Now what is Rn? Rn we have already calculated as epsilon naught h square by pi me square into n square by z. Okay, so from this I will get the value of potential energy as minus me power 4 by epsilon naught square h square, and there is one 4 here, into z square by n square. Again I have separated the constant value, and this term is the u naught. Again, u naught is the potential energy magnitude in the first orbit of hydrogen atom, and the value of u naught will be, if you look from kinetic energy, see here there was 8 and everything else is same. Everything else here is same, only here there is 4. So the denominator is 4 and there the denominator was 8, that means this value is double. So this is 27.2 electron volt, or you can say this is equal to 4.36 into 10 raised to the power minus 18 joule. Okay, so you can write U is equal to minus U naught into Z square by N square. Do not forget this minus. Potential energy at infinity is 0 and at any other point it is negative. At any other point it is negative. Don't forget this negative. Okay, that means as n increases, you will think that as n increases potential energy should decrease, but no, it is not decreasing because there is a minus sign here. Potential energy increases. Yes, the kinetic energy decreases because it is positive value. So if it is positive value, then kinetic energy will keep on decreasing, but potential energy will increase. Infinity has zero potential energy, and that is the highest potential energy. Okay, now again I will write for a hypothetical system, the energy, the potential energy will be minus xy power 4 u naught into z square by n square, and the proportionality is obviously z square by n square. For kinetic energy also it is the same proportionality, right? Now then comes the total mechanical energy. The total mechanical energy represented by E. So the total mechanical energy is the kinetic energy plus the potential energy, and this will come out to be minus the negative term is more, the positive term is less, so it will come out to be minus epsilon minus m e power 4 upon 8 epsilon naught square h square into z square by n square. Now this term is E naught, and the value of E naught is again 13.6 electron volt, because this is same as the kinetic energy constant terms. Okay, or you can say this is also equal to 2.18 into 10 raised to the power minus 18 joules. So the total energy when you add this two is equal to minus E naught z square by n square. Okay, now in standard reference that we take as infinity, in the standard reference that we have chosen for every system in this universe, the energy has to be negative. The total energy has to be negative. Why? And it has come to be negative only. The total energy has to be negative. Why? The total energy has to be negative because if the total energy is negative, then the system is in bound state, and the electron has to remain in bound state, only then it can revolve. Okay, so due to the attractive force, two things can happen. One thing is electron can get close to this is possible if the total energy is positive, or the second thing is it can revolve around it. The second thing is happening here because the total energy is negative. If the total energy is negative, the system is in bound state. Okay, it's not necessarily a circular motion, but it is in bound state. But for our case, for this case, it will be a circular motion also, right? So if the total energy is negative, the system is in bound state. It can be any closed path. All right, now the total energy is magnitude is equal to the kinetic energy, and this is equal to half of the magnitude of potential energy. The total energy is negative, the potential energy is negative, and the kinetic energy is positive, right? The total energy and the kinetic energy has the same magnitude, and they are half the magnitude of potential energy in a normal or the standard reference. Okay, now there are many things that we can discuss here. First I will write the energies again. So I'll write it only up to 4. So suppose this is the first orbit, this is the second orbit, this is the third orbit, this is the fourth orbit. Now for the first orbit, we will write the kinetic energy, we will write the potential energy, and we'll write the total energy. So for the first orbit, it is 13.6, it is minus 27.2, and it is minus 13.6 electron volts. For the second orbit, it will be 13.6 divided by n square. N is 2 square, that is 3.4. This was what we have already learned before. Okay, I told you I'll derive it, but first you have to learn it. This was what we have learned before, and now we are deriving it. So I'm writing this for hydrogen atom only, and for any other atom, you know that it is the proportionality is z square by n square. So for any other atom, you just have to multiply it with z square. Okay, obviously that atom has to be hydrogen like. So I'll write 3.4, and this will be minus 6.8, and this will be again minus 3.4. For the third one, it will be 1.51 electron volt, because 13.6 divided by 9 is 1.51, and this will come out to be minus 3.02, and this will be equal to minus 1.51 electron volt. This was what we used to remember, okay, in the previous class, right? Fourth one, you can write it yourself. I'll write 0.85, and this also minus 0.85. This will be 0.85 multiplied by 2. Okay, now as the orbit number increases, the kinetic energy decreases, but the potential energy increases, and the total energy also increases, because they are negative. 0 is the maximum for them. Okay, so as the orbit number increases, the kinetic energy decreases, the potential energy increases, and the total energy also increases, right? Now suppose instead of taking the potential energy at infinity to be 0, in any system they have taken the potential energy of the ground state as 0. Instead of taking the potential energy at infinity to be 0, if we take potential energy at ground state to be 0, you can take any point as zero potential energy, okay, because it does not have absolute value. The only thing that you have to understand here is that the difference has to be fixed, right? The difference between two orbits, the potential energy difference between two orbits has to be fixed. Okay, so I will draw these orbits again, and suppose the kinetic energy was 13.6, right? 3.4, this is 1.51, this is 0.85. The kinetic energy will not change. It has absolute value. The kinetic energy has absolute value and they will not change. But the potential energy will definitely change, and the potential energy will now be, this will be zero. Okay, according to the question, the potential energy of the ground state is zero. Now, the difference should be fixed. Listen carefully. If the difference should be fixed, that means this, the first orbit, initially it was, the potential energy was minus 27.2, but in this case it is zero. That means you have increased the potential energy by 27.2. Minus 27.2 to zero, that means you have to increase it by 27.2. So if you have increased this by 27.2, increase every orbit by same 27.2, and in that case what will you say? You will say that the difference will be fixed. So here it will become minus 6.8 plus 27.2. Here it will become minus 3.02 plus 27.2. So if you increase the potential energy of every orbit by 27.2, okay, then the difference still remains same. So the main thing that you must understand is that the difference should remain same. Okay, and the total energy, if you ask you, just add. This time the total energy can be positive also. This time this is not the standard reference. Okay, so this time the total energy can come out to be positive, and also this time this relation also will not hold. This relation will hold only for standard reference. This relation will hold only for standard reference. Okay, I'll do one more question here. Suppose potential energy of first excited state is taken as zero. In that case, what I will say, so the kinetic energy is still same, that is 13.6, 3.4, 1.51, 0.85, 1, 2, 3, 4. But the potential energy this time, this has zero value. Now this originally has minus 27.2 and this originally has minus 6.8, but now it is zero. That means you have added it by 6.8. So here also if you add it by 6.8, then the difference will remain same. The difference of potential energy always should remain same. So this will be minus 3.02, which used to be, now plus 6.8. Okay, so when you find the total energy, just add K and U. Okay, so they can give you any system.
If you like my video, do hit the like button and share my work. Also, subscribe to my channel and hit the bell icon so that you get notified whenever I upload my next video.